All right, in this video, we're going to be looking at a new type of parent function, and that's the parent function for an exponential function. So first, let's look at this graph that's below here. And this graph, as you see from your notes, is specifically for the equation 2 times 3 to the x power. And so this is an example of what an exponential function could look like. So first, let's identify some key features there. We can identify the domain and range. Now remember, when we look at a graph like this, if there's no arrows, remember we're just looking at a particular window, so this is as if we graphed it on a graphing calculator. So just because we see that on our paper that it ends at those places doesn't mean that the graph actually ends there. It keeps going infinitely up and to the right, and it keeps going infinitely to the left there. So the domain would be from negative infinity to infinity. And the range, now it's not from negative infinity to infinity because we do have an asymptote. We have an asymptote down here along the x-axis, which is where y equals 0. So down here where it says that we have an asymptote, we can say that it's y equals 0. And so that means that there's not going to be any values below that graph or below that line. And so all of them are contained to be above 0. Now they don't include 0, so we have a parentheses, remember, at 0, so we would say the range goes from 0 to infinity. Now I want you to make a connection here with the y-intercept and our equation. So here is the y-intercept, and look at our equation and see what connection you make. So hopefully you're making the connection that the y-intercept is the same as that a value. And we'll get to that, what that a value is here in a second, but that number there, that 2, is the same as your y-intercept. So our y-intercept would be the coordinate 0, 2, meaning when x is 0, our y value would be 2. So let's review end behavior. It's been a while since we've talked about that. The end behavior as x approaches infinity, so this is referring to the right side of the graph. On the right side of the graph, we see the graph is going up infinitely. And then as x approaches negative infinity, this is referring to the left side. So the left side, the graph always approaches an asymptote. So here approaches the asymptote where y is 0. So it approaches 0. So you heard me a second ago reference this letter A. This is, well, first, this whole thing here, this is the general form that's the form for an exponential function. And A is always going to be the y-intercept. Okay, so that a value is always going to be the y-intercept. Now b is very significant as well, because what we just looked at in this first example is what we call exponential growth. Now we could have other examples where it goes in a different direction that would be called exponential decay. And so if if our b value is between 0 and 1, the graph is going to be decreasing from left to right. So we would call that exponential decay. If b is bigger than 1, then the graph is going to be increasing from left to right. And we call that exponential growth. So if it were exponential decay, so if it was decreasing, instead of it going up and to the right, the graph would be going down and to the left. We would still have a horizontal asymptote at y equals 0. We would still have a y-intercept at whatever our a value is. It's just that instead of increasing from left to right, it would be decreasing from left to right if b is between 0 and 1. All right, let's look at some transformations that we could do with this graph. So we've done transformations in the past with other functions. So every transformation that we've done before applies to these as well. All right, so here we have g of x equals negative 3 to the x power. Now, in blue there, the dashed line represents our, in this case, the parent function would be 3 to the x power, which if you're wondering, well, what's a in this case? Is a 3? I don't know, what's a? Well, this is the same as saying 1 times 3 to the x power. Let's talk about that value for b and an exponent again. So remember, we've talked about exponents always being attached to a base. A great analogy is like a kid holding a helium balloon. So if a kid's holding a helium balloon, and let's say this is the parent standing next to the child holding the helium balloon, it's only the child that's holding the helium balloon, not the parent. And so we always want to make sure that there's a separation there between our base, what the exponent is attached to, and the value, in this case, a, that the exponent doesn't apply to. So in this situation, the base is 3, so that means that a is not 3. If there's no a given, we could just assume then that it's 1 because we wouldn't need to include it. So our a value would be 1, meaning our y-intercept would be at 1. And then if we need to come up with some other points, we could put 1 in for x. When you put 1 in for x, you get 3 as our answer, because 3 to the first power is 1. If I put 2 in for x, 3 squared is 9, so we would have a coordinate there at 2, 9. So that's how you can come up with a more accurate graph. All right, but now what we want to do is we want to come up with a graph for the function -3 to the x power. Now this is the same as saying -1 times 3 to the x power. Now the reason why I say that is because our exponent doesn't apply to the negative, it only applies to the base, it only applies to the 3. So if we put 2 in here for x, you might think, well, -3 squared would be +9. Nope, it's 3 squared, which would be 9, and then we apply the negative, or multiply by -1. So in other words, what's going to happen to this graph is the y-intercept would be at -1 this time, because that's our a value. But then the entire graph would be flipped. So instead of being 1, 3, it would be at 1, -3. Instead of being at 2, 9, it would be where x is 2, y would be -9. So your graph would have the same asymptote, but be flipped vertically, so be flipped over the x-axis to look like that. So the domain isn't going to change. The domain is still -infinity to infinity. Our range, though, now we have all negative values, so the range values go from -infinity, but there's none above 0. And 0 is not included because that's where our y-intercept is. I'm sorry, that's where our horizontal asymptote is at y equals 0. But our y-intercept, we said, is a point 0, -1, because it got flipped vertically. The end behavior as x approaches infinity, so this is referring to, again, to the right side of the graph. So the right side of the graph is going downwards, so we say it's going down towards -infinity. And this is referring to the left side of the graph as x approaches -infinity. So it's as the x values approach -infinity. So as the x values go to the left, what are happening to the y values? The y values are getting closer and closer to 0. All right, now we could have other transformations. So like this one here, just like any other parent function, anything happening outside the parent function is going to happen vertically. So in the previous example, what happened vertically was outside the parent function, that negative, because remember that -1 affected the graph vertically by flipping it vertically. This is going to affect the graph vertically by moving it down 4 units. So what that means is that the horizontal asymptote that was at y equals 0 is now, if I move that down 4 units, now I'm counting by 2's here, so we got to be careful. So this would be -2, so -4, 6, 8, and 10. So if we go down 4 units, -4 would be there. So that's where our new horizontal asymptote would be. Our new y-intercept, if I move that point down from being at 0, 1, if I move that down 4 units, I'd have 1, 2, 3, 4, so that's going to be right here. And the point 1, 3, if I move that down 4 units, that's going to be 1, 2, 3, 4. If I move down 9, 4 units, that's going to be at 5 now, or 1, 2, 3, 4. So now we can graph this line with those new coordinates. So that would be how the graph would be moved down 4 units. And so again, the domain doesn't change. The range changes because we moved it down 4 units. So instead of being from 0 to infinity, it's going to be from -4 to infinity. The y-intercept has changed because now it's at 0, -3 is where it crosses the y-axis. The end behavior, that's still the same as the original function because the right side of the graph is still going up towards infinity. I should say the end behavior for the right side doesn't change. But for the left side, as x approaches -infinity, instead of approaching 0, it's approaching our horizontal asymptote, which is at -4. And the reason why is because we have a horizontal asymptote at y equals -4. All right, so that's the first part. That is lesson 6.1, part A.